In this screencast, I'm going to show you how we can analyze residuals for model adequacy. In some of the previous screencasts, we created a straight line model fit for these data, porosity as a function of temperature. This dotted line shows our straight line. Some of you might be thinking, well, this straight line fit does not really fit our data that well. In other words, these errors start out positive, and then in the middle of our temperature range, they sort of go negative, and then back to positive. And this is actually a poor model because these residuals, again, the residuals, the difference between our actual minus our predicted. And so that's the difference between the markers here and our model prediction. A good model will have normally distributed residuals, and you won't see a correlation like you see here. So recall, coming up with some sort of empirical model for a real-world process. We have our output, and we can create a model. Our model prediction we compare to the output, and ideally, this error term, epsilon, will just account for random error in our process. So we'd like to determine the form of a mathematical model such that the errors are minimized in some sense and only represent purely random behavior that we are unable to predict. So if we look at the residuals, these error terms, and analyze them, we can tell how adequate our model is. And so that's what we're going to be doing in this screencast. The basic concept of residual analysis is that the model should account for all of the systematic behavior in the response variable, and what is left in the residuals is random, uncorrelated, normally distributed values with zero mean and constant error variance. If this has not been met, it indicates that the content has not been modeled out of the data, the current model is inadequate, and a better model is needed. So the question is, what steps do we take to analyze the residuals? The most common ones are graphical, and I'll be showing you how to do this in this screencast. We can create a probability plot to check normality. We can look for systematic behavior and constant variance in our residuals, a plot of the residuals versus the predicted response, also a plot of the residuals versus the input values, and we can also create scatter plots to check for correlation within the residuals called autocorrelation. So here are some examples of some of the things that we can do. As an approximate check for normality, we can construct a normal probability plot of the residuals. So this here is showing a normal probability plot of the residuals. We can also plot the residuals versus time versus the output yi or the input. And some of the possible plots that we might obtain are shown here. This first one on the left is really what you want. You want the residuals to be normally distributed, sort of random, about positive and negative. The second one here, you see that residuals start low, and then as we increase in time, or as a function of x or a function of y, the residuals start to get bigger. So residuals here are correlated somehow. Also in this third one, the residuals start out small, they get big, and then they go small again. And obviously in this last one, the residuals start out positive and go negative and then get positive again. This is similar to the example I showed at the beginning of the screencast for our porosity as a function of temperature data fit to a simple linear model. Let me show you a couple ways that we can analyze residuals. Going back to some of the work that we got in some previous screencasts, we calculated residuals here. This is also known as EI, or residual. The residual is just the difference between our observed output and our predicted, or y hat. You see here that residuals start positive, they go negative, and go positive again. Excel's regression tool has a nice way to display and analyze residuals. So I'm going to start kind of with a fresh slate here, and let's just go into Excel's regression tool. I can open up regression. Our y range is our porosity, our x range is our temperature. I don't have labels here. I'm going to create this in a new worksheet. But down here, you can click on residuals, and you can click on residual plots, and also normal probability plots. And I can go ahead and click OK. It performs the regression output for us. Let me just resize this. It also created residual plots. Here we have residuals as a function of sample percentile. You see here our residuals, they start high and then they go down and they get high again. So you definitely see correlation here as a function of temperature. That's our x variable 1. The normal probability plot of the residuals. You can't get too much information from Excel's probability plots, but this is a probability plot and it doesn't really appear to be super linear. It's better to get normal probability plots of residuals through Minitab, but we can scroll down here and we have our residuals here. This is another way, by the way, to compute residuals. You can have the regression tool compute those for you. Nevertheless, we can get some information related to residuals in Excel's regression tool. A much better way to do this, if you have access to Minitab, is to use Minitab's analysis. I've pasted my X and Y values. We're going to go up here to Stat, Regression, and I'm just going to go to Regression and Fit Regression Model. The response is my Y, so I'm going to select that. Our continuous predictors, that's just X, and I can select that. If I go into the model, right now this is just a simple linear model. So right now let's just click OK. I can go into graphs, and I'm just going to select a 4-in-1. And this is going to provide us with all of these, a histogram of the residuals, a normal probability plot of the residuals, residuals versus fits, residuals versus order if you want. And let's go ahead and do this. Let's compute residuals versus X and residuals versus Y. And I can go ahead and click OK again, and it spits out the regression output. So first of all, this is the linear regression equation. That's the same that we got using Excel. But we can scroll down here. It does a lot of things, but the important thing here for the residual analysis is the normal probability plot of the residuals. So this looks pretty good. We also have a residual versus the fitted value, and here we see that correlation with the fitted value. So on the x-axis here is actually our model prediction. The histogram doesn't tell us a whole lot for small sample sizes. It's better to use the probability plot here. But also we have versus order, we see that we have a correlation. We can also look at residuals versus X. This is what Excel gave us. And we can look at residuals versus Y. In all these cases, it's pointing to that the residuals are not very randomly distributed. And so something else should be included in our model. If your residuals look like this, if there's some sort of correlation, you can always go back and create a better model. You've already learned how to create simple polynomial models in computing. So I can go back here into regression, fit regression model, and we're going to change this now. Our model, we're going to, for example, let's go ahead and create a third order model. So this would be a third order polynomial. We can click add. Now it has x squared and x cubed. We can go ahead and click OK. Click OK again. It churns through the analysis once again. First of all, it spits out our regression equation. And we can look at the residuals. The residuals are normally distributed. We see that it's a little bit more randomly distributed for residuals versus fits and residuals versus order. There's not as much correlation. We also look at residuals versus X. So this looks pretty good, randomly distributed. There might be some issues, but we have limited sample. We only have 7 data points. But in general, this looks like a better model than our first order polynomial or a simple linear model. By the way, if you wanted to get a p-value for the residual plot here, the normal probability plot, you have to go back here into the regression tool. You have to go into storage and click on residuals. When you click on storage, it's going to output to the worksheet here in Minitab whatever you select. So I select residuals. We run this once again. So now we've output the residuals. We still don't have the p-value on our residual plot, but we can simply go back into graph probability plot. We can perform a single on our residuals now. So I'm going to select the residuals that were output. I can select that. The default distribution is the normal distribution, and we click OK. And here it's calculating a p-value of 0.525 for the residuals for our third order polynomial. So that's how you can calculate a p-value for a normal probability plot of the residuals. So hopefully you learned a little bit more about model adequacy, in particular analyzing the residuals in this screencast.